Great. Okay, so first of all, thanks for inviting me here. This is a talk about the complexity of distributions. Some of you may have seen bits and pieces of this work, and bear with me, I'm going to try to give some new stuff for each of you. Okay? So let me start with what is perhaps the simplest possible computational model, just to see a simple example. I'm going to call a function from n bits to 1 bit d local. Okay? If its output just depends on the input bits. Right? Such functions are also called juntas in learning theory or NC0 in complexity theory. Right? Can we prove lower bounds or negative results for this model? Yes, it's very easy. For example, to see that the parity function requires maximum locality, okay? Because if you flip any input bit, the output has to flip, so you must look at every bit. All right. Still, local functions, although they cannot compute parity, they can do something which is almost as good in some sense. They can sort of like pretend to be computing parity in that they can generate input-output pairs of the parity function. Okay, this is a fact that was first used, as far as I know, by Babai and also by Bopan and Lagarias in '87. Okay, so my claim is that their claim is that you can find the function that maps n bits to n plus 1 bits. Okay, so one more output bit where each output bit is 2 local, okay, just 2 local, so it just depends on 2 input bits, and the distribution of the output of the function over a truly uniform input is the same as a uniform n-bit string y together with its parity. Okay, so the function is pretending to compute in parity on some random y. And the construction is just a standard telescopic trick. Right, so these are the input bits. The first output bit, y1, okay, the y1 here, it would just x1, and then every other 2 is the XOR of 2 previous input bits, right? So if you just XOR all these things, everything cancels out except xn, which is the parity of the string. Done. Okay, that's the construction. This thing has found a few applications, like Russell and Naur have an application in cryptography, which I'm going to touch on later. OK, so the message of this line of works is that it would be nice to develop a complexity theory of distributions as opposed to functions. OK, so I want to answer questions like, how hard is it to generate or sample a distribution D, which is when you're given random bits? Okay. What kind of distributions are we going to encounter? Well, we have just seen this distribution here, y comma parity y. That's a possible distribution, or there's a whole world of distributions. One that I'm going to consider for a bit is this w sub k, which is the uniform distribution over n-bit strings of Hamming weight k. Okay, that's another one that we will see, and we will see many more. All right, so is this message new? Here is a few papers which have considered complexity of distributions in some sense or the other. So Eric Bach in '85 showed this very cute thing that you can generate a random number together with its factorization. Okay, so although factoring is believed to be hard, you can sort of like pretend to be factoring. I can give you a random number together with its factorization, which has some uses in cryptography. There is a classic paper by Trevisan Vadhan and Vasirani in which they look at various complexity classes which correspond to sampling problems. Okay? There is a paper by Embenis, Schulman, Tashma, Vasirani, and Navi, which is mostly about the quantum communication complexity of sampling, but not exclusively on that. I'm going to say it in a second. Okay, so that's indeed on the communication on the complexity of sampling. It's mostly in the communication setting. And in a section of their work on the implementation of huge random objects, Goldrake, Goldwasser, and Nussbaum actually suggest or stress the study of the complexity of distributions. Okay? So if one wants to draw a line just for the sake of it between these previous works and again our line is this one here. So we're going to get the first negative results, or also known as lower bounds, for a number of models like local AC0 Turing machines and so on. Okay? There was no lower bound that I know of, except in this paper here by Avi et al. There is one lower bound for sampling disjointness in the two-party setting, communication setting. Okay, that's the only previous bound that I know of, which in fact, of course, I found out later about it. And then we're going to revisit these problems and establish some new connections, which I'm going to see, which we're going to see in this talk. Okay. All right. So here is now a somewhat ambitious slide. Okay. You may think of lower bounds as coming roughly in three flavors. Okay. The first one is worst case lower bounds, the one that's more famous. First examples are maybe in the 60s of these bounds. And then people got really interested in average case lower bounds. Okay, and both in the conditional setting of like MP hardness, also like unconditional setting like AC0 or even Turing machines, lower bounds. And these also have fed back in the worst case lower bounds, in that you have gotten some new worst case lower bounds or some new information via this average case lower bounds. Okay, and you can think of this sampling lower bounds as a third wave, hopefully, of lower bounds. Okay, if it's very hard to sample, then it's also very hard to compute on average, and it's also very hard to compute in the worst case. Okay, for the probability notion of very hard, and hopefully this will also feed back and provide some new information on the previous ones. We'll see. All right, so here's my plan for this talk. So I want to spend a few minutes on the lower bound for sampling a specific distribution, W sub k, that I mentioned before. And then I want to discuss a connection with randomness extractors. And using this connection, go through a bunch of different models, like local again, AC0 circuits, and even Turing machines. Okay, and this we'll see both sampling lower bounds and also randomness extractor constructions for each of these. Okay, so let me start with this lower bound for sampling WK. Okay, and I'm going to try to mention open problems along the way. Okay, so here is a theorem that we proved. Here is a function that maps n bits to m bits. Okay, and the function also is 0.1 log n local. Okay, so it's about log n. So each output bit here just depends on about log n input bits. Okay. Then any such function will be such that if you plug a random uniform input to the function, the output that you get has statistical distance, which is close to 1 by a polynomial. So it's it's polynomially away from 1. So 1 is the maximum that you can know for, and this is going to be polynomially close to 1 from the uniform distribution of a balanced strings. Okay, this is the distribution of W n over 2 is the uniform distribution of an MB strings, which are balanced of exactly n over 2 ones. Okay. All right. So this is a sampling lower bound for a specific distribution. It's tied up to this omega here. Okay. You can see that just by considering the one local function identity, f of x equals x. Okay. This is one local, obviously, and standard bound on the binomial coefficients gives you a root n here. Okay. The bound also extends to W sub k, so sampling strings with different Hamming weights, and then the tightness is an open problem, and I'm going to come back to that later. And one thing that's also open that's very annoying is to remove the bound on the input length. So prove this theorem if I don't have any bound on this input length.
I don't think that's, isn't there a result of Moninaur where if you allow polynomial number of input bits that you can generate it
locally? I mentioned to him this result, and
maybe not, but maybe in AC0 certainly.
Yeah, in zero you can do a lot of stuff, and I'm gonna come back to that later. But locally, yeah, I'm gonna do it. Yeah. In zero you can definitely do it. So it's true. If you allow for more input length here, like n square, you can do it in AC0 with exponentially small distance. Do you have a question, Seb?
No, I guess the question was if allowing more inputs, I mean, why can't you just fix some of the inputs to random?
You'll see the proof, and one thing that's used in the proof. So I'm gonna you'll see the proof in a second. Okay, so before we get to the proof, I'm going to touch briefly on the connection with data structures. Okay, specifically that's about succinct data structures. Okay, so there has been some recent progress on lower bounds for succinct data structures, also by us. The most important problem that's left open is this one here, which is called the membership problem. Okay, so here is a very basic, interesting problem. So you want to store sets, okay, so subsets of a universe of n elements, okay, and think of sets of having all the same size, like n over 3, okay, so the size is fixed, and you want to store them into memories of bits, okay, and you want to simultaneously satisfy two things. You want to use an amount of memory, u, which is the optimal, okay, the best that you can afford just by counting sets, plus a small redundancy r. Okay, you want to make this r as small as possible, and simultaneously you want to be able to answer a membership question. So is this bit 1 or 0, by probing just the bits of the data structure. Okay, so you want very small space and very efficient answers to membership queries. Here the answers are deterministic.
The cases you probe are allowed to be deterministic?
They are not allowed, let's say. But even if you allow, so you can hope for data structures which have no error. You can hope for them. The ones that there are give no error, but they probe somewhat many bits. There are data structures which achieve extremely small d, like 1, and they are probabilistic. Yeah. But they've been actually randomized, and with some larger d, you can actually get them deterministic, like 100.
No, not the probing.
I think the probing.
If you want to ask one.
No one, like 100. Yeah. Yeah. Like 1, I already know it's deterministic, but 100 or like 1,000. That. Yeah. Yeah. Right.
Yeah, of course.
Yeah.
One.
Yeah. So I'm not thinking one. Okay, so there is a general connection. That if you have any solution to this problem, in fact, you also have a way to generate or sample the distribution W sub the size of S. So the Hamming weight here, so these are strings of n bits where the Hamming weight is the size of S in a way which is d local. Okay, so it's the same d in which you probe the bits, and the distance, okay, is not too bad. So it's boundary away from 1 by exponentially small in r, which is the redundancy. Yes?
So the argument here is just if you pick B1 through BU at random.
That's exactly, yeah.
You have some 2 to the negative r chance of hitting a code.
Yeah. Thank you. Yeah.
Okay.
Exactly as Russell said, this is a straightforward connection. That if you just pick the BIs at random, you have a chance 3 minus r to being in the image of some set here, in which case you're going to be uniform on this distribution. And otherwise, you don't know. Okay. Okay, so from the previous bound, as a corollary, you get that you need R amount of redundancy, which is at least logarithmic if d is like 0.1 log n. This actually is the first lower bound for sets of size n over 2 or even n over 4. Okay, so it's tight for n over 2, and for n over 4 it's not known to be tight, and that goes back to the previous problems from before. Okay. All right, now I'm going to forget about the structures and just tell you about this theorem, the proof of the theorem from before. Okay, so here is the theorem again. So if you have a function that's local, it will be far from balanced strings, and here by far it means that I need to exhibit a test t. Okay, that's such that the output of the function will be in t with probability very far away from the probability that a uniform balanced string will be in t. Okay, so my task is actually to exhibit this t and show that it achieves these bounds. Okay, and okay, let's consider a couple of warm-up scenarios. So the first one is the one in which my function is a constant function which always outputs a 0, 0, 0, 1, 1, 1. Okay, I'm going to call this the low entropy setting because the function has low entropy indeed. And here a test which works is just a test which is a support of the function. Okay, so this always the function always falls in the test, and this distribution here Wn over 2 has high entropy, so it's likely to fall in t. Done. At the other extreme, you have f of x equals x. Okay, this actually has a lot of entropy. So how do you argue here? Well, for example, you can think of the test which is a support of W over 2. So these are all the balanced strings. Okay, and the point is to argue by so-called anti-concentration that a random string is likely to have a Hamming weight exactly at n over 2. Okay, and you get the bound that you want in this case too. So the point of this is that you actually have to consider both tests, because this function here is going to kill the anti-concentration approach, and this function here is going to kill the low entropy approach. Okay, so either one of these two, it's not enough. Okay. So the idea for this bound is actually to reduce to these two cases. Okay, so how do you reduce to these two cases? You start by partitioning the bits in a certain fashion. Okay, so these are the input bits of my function, and these are the output bits. Okay, so the function is computing this way. Okay, and the requirement, the thing that I know is that each output bit just depends on the input bits. Okay. Because of that, by Markov argument, there are many input bits that will just affect order the bits.
And
okay?
you critically use the fact that the input length and the output length are the same.
That's right. So they can, yeah, that's right. They are very close to each other. So here in this fixing, it goes back to Zeb's question. This h, which is coming to the picture in just a second, I can only control its size if the input length is bounded, and otherwise I don't know how to do it. Okay, so but just to do it, okay, so you can collect an input okay, that has only degree order d, and then you collect another input which is disjoint from the which affects disjoint outputs, and so on and so forth. And what's left, you put it into H. Okay? And the point is that if you fix H, okay, all that's left, it's a bunch of blocks, and each block just depends on one input bit. Okay? So the idea is that two things can happen when I fix H. Okay? So if I fix H and have a bunch of blocks which are constant, they don't depend on this bit anymore, then I wasted a lot of entropy. This is exactly what I'm using the bound on the input length, because I cannot like waste bits, because I'm trying to hit a very high entropy distribution. So if many BIs are constant, this is a low entropy setting. Otherwise, you have many BIs which depend on the xi's, and here the idea is that since they are independent, it's likely that the Hamming weight of these things, which are chosen independently, will sum to n/2. Okay? Actually, there's a problem here because this only works if the blocks they're not different, but they have different Hamming weights. Okay? So block could be alive. Could take two different values, which however have the same Hamming weight. So in this case, the block will contribute to the entropy, but not to the anti-concentration, and it's not clear what to do. Okay. So if that's not the case, you can indeed use some anti-concentration bound, but there is this issue, and the fix is that I'm going to ask a third thing, that many blocks are all zeros. Okay. And now, if a block is all 0 and it's also alive, the other value has to have a different Hamming weight, because you only have one input, one value with Hamming weight 0, which is the whole 0. Okay, so if you have a block that's alive, it's not fixed. One of the two values is the whole 0. The other one must contribute to anti-concentration. Okay, so the final test which does it is this one here. So I'm gonna my test T. Okay, I have a challenge Z, and I have to tell you if it comes from the function or if it comes from the distribution W1/2. Okay, so I'm going to check for three things. First, I'm going to check that I could be in the low entropy case. That means that after I fix H, there's many of these bits X which are fixed, and so I just have a few strings of that type, and I can deal with those. Or there are few blocks which are all zeros. That's likely in the W(n/2) case, because these blocks are small, I can catch it, or I have anti-concentration.
So this is for an average fixing of the values to H?
This actually is a worst case. So I check if there is any fixing which gives me that value. Yeah, here is worst case. I think it would be interesting to throw in some information theory and think about the communication that I tried for a long time, and I didn't succeed. In fact, let me mention an open problem. Okay, so here is an open problem. So a general goal is that I want to understand the complexity of sampling WK. Okay, so uniform strings of weight K for any choice of K, the Hamming weight, the model. You want to do with local decision trees, AC0, and so on, statistical distance, and the randomness complexity. Okay, so I think that there's a lot of things to be done here. And interestingly, there are actually similar problems in combinatorics, coordinate theory, and ergodic theory. The main difference seems to be actually the setting of parameters. Like they don't care about the same type of asymptotics that we do. And here is one specific example that you can think about tonight. So first effect, and then a challenge. So the effect is that if you want to get very close to distribution W(n/4), these are Hamming weights n/4. Okay, I can just use a function which is too local, okay, and just outputs n's of two bits. Okay. Here I use 2n input bits, okay, and I get distance again boundary away from 1 by an inverse polynomial. And this is a triviality. And my challenge is, suppose I give you not 2n input bits, but I give you just what you need, which is the entropy of 1/4n bits. Okay, that's like the minimum. And maybe I'm going to throw in like a little bit more just to make it easier for you. Can you prove that in this case, the distance goes exponentially close to 1? Okay. I mean, how on earth are you going to get polynomially, like distance only polynomially close to 1 if you only use entropy 1/4? It seems that it's very compressed information there. You cannot extract it with just a local function. But
so if you give me anything that's omega of n, you can do it, right?
if I give you anything that's
h of quarter plus 0.0001, and
I don't know. No, I think even in this case, I don't know how to do it actually. Anything that's like 0.9n, I think I already don't know how to do it. Is there a way to do it? No. Okay. No. I don't. Yeah. So good. So I don't know anything essentially that goes significantly below 2n. Okay. But this is enough to get the data structure application, because in that case you really want to store sets in something which is very tight.
Your challenge again is with constant locality?
Yeah, even two locality 2. So each bit just depends on 2 input bits. Okay, it's hard for me to think of anything simpler than this, but this 2 local optimal input length, you want to get close to W n over 4. Yeah. Okay. Let me now a little bit switch gear and talk about the connection with randomness extractors. Okay.
So the second, in the local,
Sure.
I think I missed something. You mentioned the Littlewood offload.
Here?
So where are you using it?
Oh yeah, here. So I was just saying that if the block indeed have different sum of bits, then you can use, for example, the Littlewood offload, and then that's enough. That independent variables with different values can sum to any fixed value. Okay, let me now switch gears and talk a little bit about randomness extractors. Okay, so briefly, the setting here is that you have at your disposal a weak random source. So this is a probability distribution which makes maybe some correlation or some bias, and you want to turn it into something which is very close to uniform. This may be accomplished using an extractor, which for a family of sources or distributions S is just a deterministic efficient map, such that for every distribution in my class, if you plug a sample of that distribution into the extractor, you will get in output something which is very close to uniform. Okay, and this is stress that these are the deterministic variant. David and Noam have started this also very popular line of randomized extractors, but I'm not going to talk about that now. Starting with the work of von Neumann in the 50s, this has been a major line of research in computer science. And here is a sample of the sources that people have considered. And actually, almost all of this will also play a role for us later. So one type is the independent blocks type. Okay, so here is my source is divided into blocks of bits which are independent. So each block, like maybe has some entropy, but it's independent from the other blocks. Okay? Here, typically, the blocks are very large, and at the other extreme is when each block is just 1 bit. So this is the case of sources in which some bits are fixed to constants, and some other bits are just uniform and independent. And these are called bit fixing sources. Also, there has been some work in this model of streaming or one-way space-bounded algorithm. So these are sources which output the bits in a one-way fashion and not remember so much about the previous bits. And or sources which are uniform over linear or more generally affine spaces, say over GF2. Okay? So our results, in a nutshell, are going to be the first extractors for various computational models, like, for example, circuit sources. So sources which are output by local or AC0 maps, or even Turing-machine, I'm going to mention at the end. Okay. Okay. So let me, before we get to our results, let me discuss a paper by Trevisan and Vadhan. Okay. So they were the first to stress the importance of extracting randomness from sources which are sampled by small circuits. Okay, so they consider sources which are the usual bound on the mean entropy, so the mean entropy is k. And in addition, the output of the source is generated or sampled by a small circuit C, okay, which is given as input just a bunch of uniform bits and output a sample of the source. Okay? What they prove is that if you have an extractor, even if it has very weak parameters, like even if it gets you 1 bit from entropy almost the maximum, this implies a lower bound for the same class of circuits that you extract from. Okay, this is a relatively simple argument from a technical point of view. And you also get a converse direction that if you start with a sufficiently strong lower bound, then you get some extractors with some decent parameters. However, one issue with their work is that the lower bound that you need to start with is very strong. They themselves call it non-standard. Okay? So you need that exponential time cannot be done by sub-exponential circuits augmented with sigma 5 gates. Okay? This type of result in particular prevents you from obtaining anything unconditional, even if you start from circuit classes for which you do have lower bounds. Okay? Because as soon as you throw in essential gates, all hell breaks loose. Okay? And this stuff becomes as powerful as MP. Okay, so in a work, yes?
So you might want to point out that an extractor gives you a low amount for circuits in the sense of the earlier part of your talk, too, because it gives you a lower bound for sampling from the distribution.
Yes. I could have mentioned it like earlier, but I wanted to leave the extractor part for the second half. But yes, maybe I should have put it earlier. Yeah. So I'm.
In some sense, it's a stronger version of what you were proving before.
Yeah. So in fact, I'm going to have a slide now on this, which is maybe trivial. I mean, maybe like a technically a trivial observation. But my next thing was that extractor are. So we have made this technically a trivial observation that extractor are in fact the same thing as sampling lower bounds, however with very weak parameters. Okay, so if you have a function which is balanced, this is an extractor if and only if small circuits are unable to sample the pre-image of 0. This thing actually is not in Trevisan and Vadhan. Yeah.
I think the nice way to think of it is if you extract k bits from a source, then you get the lower bound for your k functions, so that each one is hard given the other ones. Kind of.
Is that true? So you're saying
if you have two bits of output, then for every distribution from this family, they both are uncorrelated and uniform. So even if I tell you one, you can compute. You can approximate the other one.
I see. So you're saying it's hard, like even given the previous one. So it's like advice lower bound. Yeah. I see. Interesting. Okay, I didn't know. Okay, that's a good point. Okay, so this is it's an if and no if, and it does not use these essential gates. And okay, so we just saw some lower bound. Can we get some extractors out of them? In fact, we can, but they are extremely weak. So you can like extract 1 bit from error with error at most 1 from almost maximal entropy with constant locality. And in the next slides, I'm going to vastly improve on each of these parameters.
Yeah, but there is one issue again of the input length to the circuit. In the definition of extractors, you allowed arbitrary amount of randomness. Circuits took some random string and output an n-bit string.
Right.
Whereas in your lower bounds, you allowed.
No, I'm going to give you, I just gave you one specific lower bound for the W and over thing. I'm going to prove you a bunch of other lower bounds which are independent on the things. It's just for that particular distribution, I don't know how to do it, but for other distributions, I can do it. Okay, so after this connection, I'm going to tell you about extractors and lower bounds for a bunch of models. So the first one is the local model. So once again, so here are like functions. So see that I don't have any bound on input length, which are d-local, so each output bit just depends on the input bits, and you can get this extractor here. Okay, so if you have a source with locality d, which has mean entropy k, okay, so let me set. Okay, so t is basically k, which is the mean entropy, times some polynomial in k over nd. So if you think of d as being smallish and k to be very close to n, this is basically like nothing. So think of t as k, and you can extract t bits with error exponentially small in t. Okay, so in particular, just one setting is that you can extract some polynomial number of bits when the mean entropy is sufficiently large polynomial in n, and d can even be a polynomial. Okay? And one thing to note is that you always need k, the mean entropy, to be at least d, because every source of mean entropy k can be written in a k-local fashion, and it's impossible to extract from k-local sources in general. Okay? Okay, so if this is a constant, here you get extractor for NC0 sources, which was independently done by Day and Watson. Okay, so how do we prove these things? So the high-level proof actually is just a reduction. Okay, so we prove a result that the sources that I'm interested in fact, I can write them as a convex combination of a different type of source, which I call bit block. Okay, with parameters which are, the entropy of this source is this t, the error is exponentially small in t, and the block size, which I'm going to explain in a second, is d over k. Okay, it's the value of 4. So bit block source is just like a bit fixing source. Okay, so some bits are fixed and others are variables, but the only difference is that these variables can be repeated. Okay, how many times can I repeat it? I can repeat it most is block size parameter, which here is d over k. Okay, so each bit is either constant or it's a variable, or maybe it's a variable complemented, and I can repeat bits a few times. Okay. This happens to be a special case of low-weight affine sources, which were introduced and studied by Rao, who gave very good extractors for them. The extractor from the previous slide can be obtained by plugging this theorem together with Rao's extractor. Okay? However, this extractor appears to be somewhat of an overkill. So one open problem here is to get a different extractor, which is hopefully simpler just for bit block sources. Okay? And I don't know anything, even if the block size, which is the number of repetition, is 2. I mean, I don't know anything which is different than this. Okay? So that's another problem. Okay, so now I want to spend some minutes on how we prove this reduction here. So I have this technical slide which is one of our main technical contributions. Okay, so what's going on here is that I have a d-local source of m bits, which has mean entropy k, and I want to prove that it's a convex combination of these bit block sources. Okay, so here is my input to the source, this bits x, and this is the sample. These are the output bits. So how do we do this reduction? First, I'm going to use the same trick as before about the degree. So I know that each output bit just depends on the input bits. Okay? So like before, by Markov argument, many input bits have degree about order d. Okay? So in fact, here in this setting, like things are a little bit different because without loss of generality, I can assume that every bit here has degree at most nd over k. Why is that? Because the number of bits which has higher degree is about k, and if I just throw away these bits, I've not affected my mean entropy by much. Okay, and I'm not shooting for like a very tight relationship on the mean entropy. Okay, so some bits could affect all the bits here, just fix them, and you just lose a little bit in mean entropy, which doesn't matter. All right, so now you do this kind of very iterative argument. Okay, so here is one step. We know that the output entropy is at least k. Okay, so there has to be some bit somewhere which has variance at least k over n. Okay, so by variance I mean that both 0 and 1 are obtained with probability at least k over n by 1. Okay, so it's it's somewhat unbiased. This step is true because if every bit had small variance, then every bit will have small entropy. And if you switch to Shannon entropy, which bounds the mean entropy, you will actually contradict the bound on mean entropy of this sample y. All right, now I have a bit here which is somewhat unbiased, okay? And it only depends on the input bits. So now I can apply an argument which is known as isoperimetry, okay, which says that some input bit here must have somewhat large influence on this bit here. Okay, so this follows from the standard isoperimetric inequality. I have a bit, let's say xj, which has influenced at least the variance of this bit divided by d, which is how many bits this y depended on. Okay. All right. So I have this bit here. So now set uniformly anything else that could possibly affect y. Okay. Set these guys uniformly at random, and also fix for later purposes the So okay, so you basically fix, so you have this xj, you fix the neighborhood of xj except this bit here, and also the neighborhood of that neighborhood. Okay, this is to avoid the later correlations. Okay, so when I do this fixing, since this bit xj had an influence with probably at least the influence, which is k over nd. This neighborhood of this xj here is not fixed. Okay, it's non-constant, and what's not fixed is this bit yi here. Okay, so I got my block. This is my block from the bit block source. Okay, the neighborhood of this guy here, it's non-constant because at least this bit is non-constant and has small size by this bound here. And then, like since I fixed the neighborhood of the neighborhood, I'm also allowed to repeat this argument, and I'm going to iteratively find new blocks. Okay, each time I'm only like fixing this neighborhood of the neighborhood, which is not much, and that's all the entropy which I'm losing. So I can repeat k, which is my initial entropy, divided by the size of the neighborhood of the neighborhood. And by chain of bound with high probability, most of these blocks will be alive and will give me my high entropy bit block source.
So why is it bit block source exactly?
So what's alive? So you have a bit which has high variance here, and so there's an input bit here which has high influence.
So you leave it alive, and
I fix the stuff here.
That's everything in its neighborhood of neighborhood.
Yeah. So
This you leave alive.
I fix the stuff
So
here.
This is a bit that will occur.
Yeah.
At most nd over k times somewhere.
Which bit? This.
No, the input bit.
The influential.
Yeah, the
The
influential.
influential bit will occur.
Oh, yeah. That's right. Yeah.
But don't you need this, like, you said you're choosing the non-influential bits at random,
The values.
the values.
The values.
Yeah.
The set you don't
Fix them at random. So
just giving you a Comics combination, or
yeah, because I fix them at random. So
you might lose this like statistical distance, right? For many fixings, the bit might not be influential.
so here actually I'm not getting anything possibly for statistical distance. I just prove this convex. So, like you're asking about the sampling over bound.
No, I'm talking about like say convex combination of
Yeah.
block sources, but you don't get this entropy, high entropy bound for many of these.
No. The entropy bound comes because each time a block is going to be alive with probability at least this, which is the influence, and I have a trillion blocks. So by chain of bound, many of them will be alive. Yeah, it's because I many of them. If I only had one, I would like shoot myself. But there's many of them, and there's many more blocks than the probability of one being alive. Okay. So that's how you. This is the result for local sources. And one open problem here that I want to mention that I've been thinking about, but okay, does the previous result hold for decision tree sources? Okay, so each output bit I want it to be not of d local, but a depth d tree of the input bits. Okay, so you query a bit and then you do something else depending on the bits. One major ingredient before was the use of this isoperimetric inequality. In fact, there is one which works just as fine for decision trees. Right? It's a very nice result. O'Donnell, Sachs, Sham, and Cervedio. So what goes wrong? Somehow this at the beginning, when like you fix these bits which have high degree and you throw them away, you can do that for local sources. For the decision trees, this notion disappears and gets more complicated. But I think it's not impossible to prove either the same thing for decision tree or prove that it's impossible. That, like, if you can like show me one decision tree source which is not a convex combination of high entropy bit block sources or even affine sources. Okay. Okay. Let me go to EC0 circuits.
You can just use, now you allow yourself a lot of input random, the randomness is large. So don't you get the random restriction for free in some sense in there?
Yeah, that's right. You get them for free.
You reduce it to local.
Good. Okay. So yeah. So good. So you can do something, but you have like a loss in the parameters because of the to reduce it to local. So to make it local, you lose like correspondingly in the error. So I want to extract directly from Okay, so for binary circuits, I'm going to use what I've already mentioned. So the decision tree will actually improve the parameters of this thing. That's one reason for doing it. Okay, so this is a constant depth circuit. You've all seen it. We can also extract from the circuit. So if you start, if this is my sample, which is output from a random input, has entropy k. I'm going to extract about k bits. Okay, k is some polynomial with error. So the polynomial is small, and if you can extract from the decision tree, you're going to make this thing exponentially small. So that's where it kicks in. So how do we do this? Apply random restriction, as Avi was saying. So the idea is that by the switch lemma, the circuit is going to collapse to a local source, and then I'm going to apply the previous extractor. Okay. One problem is that when you apply the switch lemma or random restriction, you're going to fix the vast majority of the variables. So conceivably, you could have lost all your entropy. So we prove that in fact, the best that you can offer is true. So here is about any function whatsoever. You can forget about AC0 if you have any function which has mean entropy k. Okay. If you hit it with random restriction where each variable is alive with probability p, with high probability, the restricted function has mean entropy p times k. This is the best that you can offer, because if I start with the identity function, I get exactly this bound here. Okay, and here, so the parameters, you can set this p to be like polynomial in the mean entropy, and you get the result. Okay, let me tell you how this is proved. So the proof of this restriction result builds on a paper with Lovett, which proves sampling lower bounds for the Z0. And what was done there was stressing the importance in this context of a specific isoperimetric inequality for noise. Okay. So what does this thing say? It says that if you have any set A whatsoever which has density alpha, now think of choosing a random string M, and then also after that of choosing a string M prime, which is obtained by flipping bits in M with probability P. Okay, so it's a noisy version of M. M prime is a noisy version of M. And then let's say I'm interested in the probability that both M glance in A and also M prime glance in A. Okay, so these are two correlated inputs which both need to fall in A. Okay, okay, so if M and M prime were independent and uniform, this probability was where it would be exactly alpha square. And here in this noisy version, it's possible to prove this bound here. First, alpha square is still a lower bound. It's actually it's very easy to prove this compared to the other one. And also using the hypercontractivity, this probability is bounded from above by alpha to the 1 plus b. Okay, so you get this extra factor of alpha to the p. So p was the parameter with which you are flipping bits in M prime. Okay, actually, there is actually a more general quantity here which makes it tight in the case that p is half. So using this bound, actually, it's possible to bound the collision probability of the restricted function. Okay, and collision probability has some relationship with the, I mean, is also a lower bound up to constants for the mean entropy. Okay, because basically f restricted to R, it's like, you know, the bits in M which I don't flip are those in which are not star in the restrictions, and the other ones are independent. So that's how this thing is proved. Okay, here is another thing. Okay, so a corollary. So in particular, we can get the first sampling lower bounds for function by AC0. Okay, so I can give you an explicit Boolean function f where that AC0 cannot sample y, comma f of y. Okay, so what's f? F is any bit of any affine extractor for a mean entropy k to the n to the 0.9.
So the work with Lovett gave a sampling lower bound with the...
Yeah, that's right. So the work, yeah, that's right. Thanks. So the work with Lovett actually gave something where f was not Boolean. Okay, just using the previous isoperimetric stuff and noise sensitivity, and using this other little bit of machinery, we actually get this 1-bit version. Okay, so this is somewhat interesting in relationship to the work by Russell that I mentioned before. That okay, so here basically I cannot sample f if the entropy is somewhat below n. Okay, so n to the 0.9. Actually, if k is above n over 2, then inner product is a 1-bit affine extractor. Okay, that's the first example that people give. And it's possible to see that the 0 can sample y inner product y. Okay, it was shown by Russell right now, like building on this result by Babai that I mentioned in the second slide. Okay, so you can take this maybe as an explanation of why in affine extractors, when the entropy goes small, are more complicated. Okay, you can't even sample them in AC0. Okay. So, okay, an open problem for review is something that I spent a lot of time on. Okay, this actually goes back to what I was saying also. So it's possible to show. Actually, this is not in Naur's paper, as far as I know. It's for an early paper, but anyway, it's possible to show that AC0 can generate y comma majority of y with exponentially small error. Okay, so on the second slide, I showed you how just with locality 2, you can generate y parity y. And here, if you go to AC0, you can even generate y majority y, which seems much more powerful. Okay. However, I only can do it when the error is exponentially small but non-zero. Okay, the challenge is, can you make error 0 in this result, or is it impossible? Can AC0 generate exactly y majority y? I don't know. Here is a question which seems to have some relationship with it, and we thought about together with Shagar. Okay, this is just combinatorics question. So think of the hypercube on n dimensions. Okay, and think of just the upper half, okay, the triangle, the upper half of the hypercube with one more dimension. Okay, so these two sets actually have the same size. Okay, this is a basic fact that people do in high school. Okay, fine. Suppose that I have any bijection that goes from here there. Okay, the same size, so it should be a bijection. Can you prove that any bijection must have large expected Hamming distortion? Okay, so if you map an edge there, the edge must sort of like delay by a lot. Okay, it doesn't seem to be out of this world, but we weren't able to do it. And if the stronger the bound that you get here, the more powerful the model you can rule out for doing that. Okay, I don't know this thing is exactly equivalent to the problem there, but it seems close. Okay, so the catch here is that AC0 or local functions have very small Hamming distortion. Every map in AC0 or local function have very small Hamming distortion. So if you prove this bound, you get a sampling lower bound. Okay, let me just take a couple of minutes, maybe like 1 minute, about Turing machines. This is actually a new result. Okay, so Turing machine source. So I want to think of machines. So these are Turing machines that start on all blank tape. So you can think of them as all zeros. And the machines, this is the tape. The machines have a coin toss state. So as soon as they enter a state, the machine writes a random bit under the head. Okay, so you don't take an input, you just use random coins. So the machine is going to like run for yes.
So the random output tape is a write-only tape? Or
No. It's read. Yeah, this is read and write. Read and write. But it starts all blank, and then you can start writing down random bits, and you can also read them and change them any way you want. Okay. So it's going to run for a while, and then at some point it's going to stop, and it's going to output m bits, and that's my sample. Okay. So can anyone see in 3 seconds an extractor for the source? Zev.
No, can you first write the random string somewhere, then compute some function of it and write it in the first n bits?
Compute some function. I mean,
Just go write
this has a bound on time, of course. I mean, n square, about n square, which is the best that we can afford for.
I'm saying you can write a completely random string from position n to 2n.
Yeah, you can.
Then compute some function of it.
By a Turing machine.
In n square time by Turing.
Yeah.
you have only one tape for your random.
Yeah.
Because like
You can
the important thing is a random tape is just one tape. And
Sequentially.
You have sequential
Yeah,
access
yeah.
to it. So it must be palindromes.
Yeah, so you can take in a you break it to 2 parts and take in a product.
That's right.
Communication complexity is small.
That's right. So that would work. So you can get this type of extractor actually that you can get. So the machine will run in time n to the 1.9, which is the best that we know for. After like more than 40 years, as you know, you can extract a polynomial number of bits with exponentially small error. Okay, so you can either like do a communication complexity, as Avi was saying, but there's actually a couple of variants. So you can actually prove that the Turing machine source will be a convex combination of independent block sources, and here there's a couple of differences from the usual settings. So the first is that this thing actually has no error. Okay, so the cross-in sequence technique for combination complexity actually has an error polynomial, and which is still an open problem if it can be removed, and the sampling setting you actually get one with no error, so it's a bit different. And also we benefit from sampling, from having like multiple blocks, okay, but it's still just a combination. And once you have this setting, you can, for example, like hit it with an extractor by David, Kamprau, and Vadhan, which extracts from these things. And this also gives as far as I know, the first sampling lower bound for two machines, so that you cannot sample xy in the product of xy. The same technique, just use the extractor by Shor and Goldner, which is in the product. Okay, I'm 1 minute over time, so this is just my summary. Complexity distribution is uncharted research direction. We have seen a bunch of connections to structures, randomized extractors, various performance in combinatorics, and there is first extractors and sampling lower bounds for a bunch of models here. Thanks.
Questions?
Yeah.
These sampling lower bounds go away as soon as you have two tapes.
You're asking if sampling lower bounds are impossible when you have two tapes?
I mean, what
Yeah.
happens there?
Yeah, so there is a fascinating number of variants of Turing machines, and the point is that even for two tapes, linear, what's that?
Like with multiple heads.
Two tapes, two heads, like nothing is known. Like order n is the best lower bound. I mean n is the best lower bound. So the only case essentially in which you can put a bound is like single tape, or maybe you can do one tape which is read-only, and the second one which is read-only, then maybe you can do something. But this is basically the state of the art still. After I think 66, it was done. This, yeah. Yeah. Oh yeah.
You mentioned the Vadhan.
Oh yeah.
Now people try to design sampling algorithms for all sorts of
Right.
situations. Somehow, would theory extend to that, or
Yeah.
imply something?
Yeah, that's an excellent question. Thanks. So there is a large body of works on which is closer to like MP hardness, in which you want to put, maybe sampling sub formulas with certain parameters is hard.
I mean, using the self-reducibility for these things.
Right. Yeah. So that's a very interesting thing, I guess. If one wants to draw a line, which is very simple, is that here we focus on unconditional lower bounds. So all those works focus about connection. If I could sample, I could do something else, but nobody knows anything. But those things are more relevant to like algorithmic questions often. I don't know of any specific connection. There has been some works on like using local function to sample, like for example, if you have a computer and you want to sample biased distributions for your algorithm, and you want to sample like very fast, then actually lower bounds may play a role. But for these more complicated structures, I don't know of any. Like usually when you go for unconditional lower bound, it's very simple type of structure like parity in the product. Majority is what you can do. But hopefully in the future, yeah.
So the extractors for low degree polynomials, but
Yeah.
with two polynomials over GF2, that's still open, right?
It's still open, and this maybe this line of work points out to a specific conjecture. What about we do inner product or generalize inner product?
So the Turing-machine model doesn't come closer to some kind of low degree polynomial?
No, I don't think so, because probably x1 times xn, and every machine needs to shuffle all the way there.
Some limited dependence between the variables, or
I don't know. Yeah. I've been thinking for a while if you can prove that this thing here, like x1 times x2 times x3 plus x4, x5, x6 plus plus. This is a generalized inner product. maybe that's an extractor, 1-bit extractor for degree 2 polynomials with mean entropy 0.99. Right? This is something which, right, in terms of like average case hardness, this is good. But for extractors, I don't know. But it doesn't seem to be impossible to do it. But yeah, that's. I don't know how you would sample that with a degree 2 polynomial well. Okay, thank you.